Hi everyone, this is Kanika, and in this video we are going to discuss a hard level LeetCode problem which is merge k sorted list. So in this problem we are given k linked list and these linked lists are sorted in ascending order, and we need to merge all these linked lists into one sorted linked list, and we need to return this. For example, let's see this case. We are given an array of linked lists. So basically these are the three linked lists given to us, which is 1, 4, 5, 1, 3, 4 and 2, 6. So we need to merge these three linked lists. These linked lists are sorted in ascending order, and so we need to merge these linked lists in a single linked list. And for example, in example 2, if the list is empty, we need to return empty. Third case can be our array of list is not empty, but the list inside that array is empty. So in this case also we'll return empty, right? Okay. Okay, so here k is given as 3 because there are 3 linked lists and we need to merge these 3 linked lists. So first approach, we'll discuss a super naive approach. We'll not discuss all the approaches, though there can be multiple approaches to approach this problem. So the super naive approach can be that what we can do is we can copy all these elements into a single array. So we'll copy all these elements 1, 4, 5 and then element of another list 1, 3, 4 and then another linked list which is 2, 6. We have copied these into an array, suppose, and after that we'll sort the array, and after sorting our array will look like this: 1, 1, then 2, then 4, 4, 5, 6, 3 also. So we got the sorted array. After that, convert this array into the linked list and return the linked list. So we need to do this. So what will be the time complexity for the super naive approach? See, firstly, we are traversing every node of each linked list so that we can store all these nodes in a single array, right? So for traversing these nodes, supposedly the maximum number of nodes in a linked list is n, right? So we need to traverse n number of nodes. So for traversal, we'll take big O of n time, and for sorting, then we need to sort this also. For sorting, we'll take big O of n log n time, and then again we need to traverse this array so that we can convert this into our linked list. So again we'll take big O of n time. So we can say that we'll take total of n log n big O of n log n time. So the time complexity for this approach is which is big O of n log n, and the space complexity would be big O of n, right? So this is a super naive approach. This is the approach 1 which we just discussed. So now question comes that can we do better than this time complexity? Of course we can do better than big O of n log n. We can solve this question in big O of n log k time. So in order to discuss the solution for big O of n log k time, you need to understand that there can be multiple approaches to this question. So this is the approach 1 we have discussed. What will happen in approach 2 is, let's discuss approach 2. What you can do is you can make use of a problem of merge two sorted lists. So we can take at max 2 lists at a time and we can merge them together. After merging, we'll get a single linked list, single sorted linked list, and then we can merge that linked list with another one. So after merging these two linked lists, we'll get a linked list which is sorted, and we'll take this linked list and this linked list together and then we'll merge it. So we have to keep on repeating this process to merge all these k linked lists. So we need to repeat this process k minus 1 time, right? Again, so this can be one of the approach, but again this is not the efficient solution. All right, so it's time to discuss the efficient approach. So we are given 3 linked lists, k as 3, and we need to merge these 3 linked lists. So what we'll do is we'll make use of min heap. We'll make use of min heap. So there can be two approaches using min heap, and we'll discuss the efficient one here, which will take big O of n log k time. Alright, so in this approach, what we'll do is we'll add the first node of every linked list in our min heap. So our min heap will contain 3 nodes, which is 1, 1 and 2. So, and we'll also maintain a node, dummy node. We'll also maintain a dummy node to keep track of our linked list head, which we'll need to return, right? And we can maintain a variable current so that we can make the new node as current.next. So what we'll do is we'll remove the first node of min heap and make it current.next. So this is current.next is our new node, which is the removed node from min heap. and we'll move current to the current dot next, so that next time when we'll have to attach a node, we'll attach it by saying that current dot next is the new node, right? So this is the node which we have removed. Now we need to move our pointer to the next node, and we need to add this node in our min heap. So currently our min heap has only two elements, which is 1 and 2, and we need to add this 4 also in our min heap, right? Again we'll repeat the same process. We'll remove the top node from min heap, we'll attach it to the current dot next, and we'll move this current, right? So since this one has been removed from our min heap, that means this one has been traversed, and now we need to move our pointer to the next node. Again we need to repeat the same process, and currently our min heap has only two elements, which is 2 and 4. So we need to add this 3 also to the min heap, right? Again we need to repeat the same process. We need to remove the top node from our min heap and attach it to the current dot next, and we need to move the current as well, right? So this time this node has been used. Now we need to move our pointer to the next node, and we need to add this to our min heap. So our min heap will look like this: 3, 4, and after adding 6 it will look like this, right? Again we will repeat the same process. We'll remove the first node from the min heap, attach it to the current dot next, and we'll check from which list we have removed it. Since this node has been traversed, we'll move our pointer to the next node, and we'll add this 4 in the min heap. So our min heap will look like this: 4 and 6 is already in the min heap, and we are adding this 4 also, right? Again we'll repeat the same process. We'll remove the top node, we'll add it, and we'll move the current also, right? So since we have used this also, we'll move the pointer to the next, which is null in this case, right? So we'll not add anything this time to our min heap. Our min heap has only two elements, which is 4 and 6 this time, right? Our min heap has only two elements, 4 and 6. What we'll do is remove the first node from the min heap and make it current dot next, and move the current to the next, right? Alright, so this 4 has been traversed. Now we'll move the pointer to 5. Now we have to add 5 to our min heap. So what we are doing is we are repeating three steps, which is first remove the top element from min heap, add it to the list, and then add the next of the traverse node to the min heap. So we need to add this 5. Currently our min heap has only one element, which is 6. And after adding 5, our min heap will look like this: 5 and 6. Why 5 is at top? Because we are maintaining min heap, and every time the top of the min heap will contain a node which has the smallest value, right? So this time 5 has the smallest value. Then we'll repeat the same process. We'll remove the first element from the min heap and make it as the current dot next, and we'll make current as current dot next, right? Okay, and we'll move, since this 5 has been traversed, we'll move our pointer to here, and we have reached null. So this time we'll not add anything to our min heap. So our min heap will contain only one element, which is 6, right? So what we'll do is we'll again remove the top element from min heap and add it to the current next, and we'll make current as current dot next, and we'll move this pointer to null. So now you can notice that we have traversed all these three linked lists, and we have got this linked list which is sorted, right? So what we'll do is we will return this as a new head, which is dummies.next. So we'll return dummy.next as a new head. Alright, so let's analyze the time complexity for this approach. So you will notice that each time we are inserting at max k elements in min heap. So we are inserting and removing k elements to and from our min heap. For inserting and removing k element, it will take k log k time. For maintaining min heap, we need to do this big of k log k operation for each node. So if the maximum number of nodes in a linked list is n, that means we need to repeat this k log k operation n times. So we can say that the time complexity would be big of n log k. So we need to perform log k operation, k log k operation n number of times, and since n is the maximum number of nodes in a linked list, so we can say that big of n log k is the time complexity. And what will be the space complexity? Since we are storing at max 3 nodes, that means at max k nodes we are storing. That means we can say that space complexity is big of k, because our min heap will only contain 3 nodes. So our priority queue will only contain k nodes at a time. So our space complexity is big of k. So if you have any confusion in time complexity or space complexity, I'll give a detailed comment for this time and space complexity in the code. So let's discuss the code. So what we have done is, so this is a function which we need to complete, merge k list. So first we'll check whether our list is empty or not. If our array of list is empty, like in this case example 2, if this is empty, we have to return the empty list. So first thing we need to check is whether our list is empty. If our list is empty, then we need to return null. Okay, in next step we have created our min heap, which is priority queue, and by default this is min heap in Java, and we need to pass the comparator as well. So I have created a comparator. So what is a comparator? I hope you know about comparator. So what this comparator is for? This comparator will compare two nodes based upon their values. So that our min heap can contain the node with the smallest value. So this comparator will arrange the nodes in the sorted order of their values, right? So I have created a comparator here. So this is a class I have created, extended list node class, which will implement comparator. So in order to pass the comparator in the priority queue in our min heap, we need to implement a comparator interface. So this is a comparator interface of type list node. So this is a list node class which has already been declared, right? So we need to implement the comparator interface of type list node, and we need to override one method for the comparator interface, which is compare, and it will take two nodes, node 1 and node 2, and it will return the nodes in sorted order. So you need to keep two things in mind. Either we can use either we can implement the comparator interface, or we can implement the comparable interface in order to pass the comparator, right? So here we have implemented the comparator interface. We can also implement comparable interface. The only difference is here we need to override the method compare, and here we need to override the method compare to, which will take only one value. Here it will take two parameters. So I have overridden compare method, which will sort the nodes according to the values. So I have passed the instance of this class extended list node, which will implement comparator, right? So this will create our min heap, and this will sort the nodes according to their values. So firstly, if you remember, we have stored the first node of each linked list. So this is what we are doing in this case in line number 21. So we have stored the first element of each linked list. So we are traversing through the list. Suppose they are k list, this loop will run k times, and we'll check whether the list is empty or not. If the list is not empty, we'll store the first element of each linked list to our priority queue, which is min heap, and then we'll call the merge list function, which will return the combined sorted linked list. So this is a helper function which we have created. We have passed the priority queue, we have passed the list array, right? What we have done is we have created dummy, and we have kept a pointer which is current on the dummy node, right? What we'll do is we have to remove the first node. We have to remove the first node from linked list, and we'll store it in a node. So here also you can see we have removed the first node and we have stored it in a node. So what we have done is we have removed the first element from the min heap and we have stored it in a variable node, and we have pointed the current dot next to the node so that it has a connect to the created node, right? So our current was initially a dummy, and we have created a node which is node. So our current should point to the node. So this is what we have done in this step. And then we have moved the current by 1, which is current, we have moved it by 1. We have made current as current dot next, and we'll check whether the next of this node which we have removed, is it null in our linked list, in our linked list array. So what we'll check is whether this node is null or not, whether this pointer pointing to the node is null or not. If this is not null, then we will add this to our priority queue. So we have added this to our priority queue if this is not null. And we'll keep on repeating these three steps again and again until our min heap is not empty. Once this is empty, we'll need to return the new head, which is dummy.next. So in order to understand the time complexity, what we can do is this would be big O of n plus k log k, which is big O of n log k you can consider, because big O of k log k is for adding the first k elements in min heap, right? And big O of n log k for this merge list function, which will create the linked list in a sorted order. The first k elements we have already added in the priority queue, and after that we need to add remaining n minus k elements, but this will take big O of n log k time, and we now need to remove these n elements from our priority queue, and this will again take big O of n log k time. So adding and removing the elements from our priority queue will take big O of n log k time, right? So overall we can say that it has the time complexity as n log k, right? And space complexity as big O of k, because our priority queue would contain only k nodes. So this was the solution for this problem, merge k sorted list. So if you have any doubt, please comment in the comment section below. And thanks for watching. See you in the next video. Bye for now.